Okay, Chem, today we're going to learn how to do orbital box diagrams. These are another type of electron configuration that actually accounts for not only off-ball principle, but Pauli exclusion principle and Hund's rule. So off-ball principle is that the electrons will fill in order of increasing energy, and we do that with all of the electron configurations. But Pauli exclusion principle states that for two electrons to occupy the same orbital, they must have opposite spins. So that means that each orbital holds a maximum of 2 electrons, but they have to have opposite spins. And then Hund's rule states that electrons will fill in the lowest energy possible configuration, meaning that in a sublevel, if there's more than one orbital, each orbital will get 1 electron before anybody doubles up. And I will illustrate that for you. So let's just do some electron configurations together. I'm going to pick one that we haven't done before, and that's selenium. So selenium is number 34, so it has a Z number. Of 34. So I'm going to do the complete electron configuration first with 34 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I now have 10, 20 electrons represented, and next I go to 3d. 3d 10, now have 30 electrons, and then I'll go to 4p, and that only has 4 electrons. So that's my complete electron configuration. Now remember, when we're doing abbreviated electron configuration, we go back to the previous noble gas or the previous full electron shell. Remember, my electron shells end at 1s2, 2p6, 3p6, 4p6, and 5p6. So I'm going to go backwards to 3p6. If I look on my periodic table of the elements, I will see that 3p6 here is argon. So when I write argon in brackets, I'm going to represent all 18 electrons that belong to argon. And I still need to put the outside electrons. So all of these are my outer shell electrons. This inside here, this is my core. All of these are my outer shell electrons. And then my valence electrons, if you remember, you find the highest principal energy level. We've got some 1s, some 2s, some 3s, some 4s. 4 is the highest one, so I'm going to underline them all. So I have 6 valence electrons. And the valence electrons are 4s2, 4p4. Now, let's use all this stuff, and you don't need to do all of this to represent the element in an orbital box diagram. You just need to represent 34 electrons. So Pauli exclusion principle means that in the same orbital, the electrons have to have opposite spin. We represent, in this model, electrons with an arrow. So I have one arrow pointing up and one arrow pointing down to follow Pauli exclusion principle and represent the fact that the electrons have opposite spins. Now I'm going to fill this guy. Now watch how I fill 2p. Because of Hund's rule, each orbital gets 1 electron in the 2p sublevel before anybody gets 2. So see how I fill them up? And same thing with the D sublevel. Each orbital holds 2. There's 5 orbitals. Each orbital will get 1 electron before you put 2 in there. That's Hund's rule. Now we go to 4p. 1, 2, 3, 4. So the orbital box diagram is good at helping us represent the fact that there's 2 unpaired electrons in selenium, and 2 of the orbitals are only half full. If you did not use box diagrams, the 4p4, that might suggest to you that there was 2 pairs of electrons in that last sublevel. But there's not 2 pairs. There's 1 pair and 2 single electrons. This is going to become important later when it comes to bonding. Okay, now that you've learned a little bit about orbital box diagrams, I'm going to do first a little one for you and then a really big one, where I'll probably have to add some more boxes in there. So let's do a little one in nitrogen. Nitrogen has a Z number of 7, so he's got 7 electrons. His complete electron configuration is 1s2, 2s2, and then the last shell contains 2p3 electrons in the 2p. I don't have the 2p full, so I don't write 2p6. I don't have that many electrons to fill it up. Now let's do the abbreviated version. The abbreviated version has the core in brackets. The core is the previous noble gas. In nitrogen's case, that's helium. So inside the brackets this time are only the core electrons, which are the 1s2 electrons. The outer shell electrons in this case are the valence electrons. The valence shell is the 2s2, 2p3. So now let's put the arrows in. Remember, they're pointing opposite ways because Pauli exclusion principle states that they have to have opposite spins. How we indicate that in this model is we put the arrows pointing in opposite directions. And then when we get to 2p, Hund's rule tells us that we fill up 1 electron in each orbital before we double up. So this would be how you would indicate your orbital box diagram for nitrogen to accommodate for Pauli exclusion principle and for Hund's rule and off-ball principle. This also tells us that nitrogen has 3 unpaired electrons. And these 3 unpaired electrons is why nitrogen usually forms 3 bonds. So we'll learn about that in the future. Next, I'm going to do a big one for you. Let's do platinum next. You find platinum in the transition metals. He's one of my favorites. He's very pretty and very shiny, along with titanium. Titanium is also a really good one. Of course, not to diminish the fact that we can't live without oxygen, and carbon is a backbone of all the DNA that we have, so on and so forth. But I just like the way platinum looks. So Z number of 78. So I'm going to do the complete electron configuration real quick. Let's count so we can see where we're at. 10, 20, 30, 36. So if we were at krypton, we'd be done now. After 4p comes 5s2. Notice the boxes that we draw have to have the sublevel written underneath there. The sublevel is the combination of the principal energy level with the orbital shape. 4d10, 5p6, 6s2. Let's count now. 10, 20, 30, 38, 48, 54, 56. So I would be at barium right now, and next after 6s I go to 4F, 14. And then after 4F, I didn't draw enough boxes here, but after 4F, we're going to go back to 5D. So this is how I usually draw my boxes. D gets 5 boxes for 5 orbitals to hold 10 electrons each D sublevel. So we're at 5D. 4F, 14, and let's count 10, 20, 30, 38, 48, 56, and then we're at 70 right now, so we need 8 more. So it'll be 5D8. That's the complete electron configuration. If I go back to my previous filled shell, that's 5p6. At the end of 5p6 is xenon 454. When I put xenon in brackets like this, that's all 54 electrons that represent xenon is in there. And then I still have to represent my outer shell electrons. So this is the abbreviated configuration right here. In order to find the number of valence electrons, I underline the highest coefficient or the biggest energy level, and that's 6s2. All of my D block and F block elements have 2 valence electrons technically. They'll all have those 2 outer shells. So this is going to be lots and lots of arrows in order to fill up all 78 electrons that I need. I indicate my arrows this way just because it's a lot quicker. And don't worry, I won't give you too many problems where you have to do this many electrons, but it's no big deal when you know how to do them. That's all we need to know, is that we know how to do these big ones along with the little ones. And then this last shell, we're going to be careful because it's 1, 2, 3, 4, 5, 6, 7, 8. And because of this, because of Hund's rule, we see that we have 2 unpaired electrons in platinum. And that's how you do the orbital box diagrams.